Dear students, in this video lecture we are going to discuss the concept of memory interfacing with 8085 microprocessor. This typical block diagram we have already discussed, that is microprocessor based system which consists of the input peripheral, output peripheral, memory element and power supply. So in today's lecture we are going to discuss how to connect or how to interface the memory device or memory element or memory IC with 8085 microprocessor. So before moving towards the memory interfacing with 8085 microprocessor, we will see various signals of memory IC or memory device. So here in these two diagrams we can able to see the RAM IC and ROM IC. RAM means random access memory and EEPROM means electrically programmable read-only memory, that is ROM IC. We will see the various signals of these two memory devices. So here N indicates the number of address lines. These are the input signals to the memory IC. In both ICs you will find these address lines. So depending on the memory capacity you will find the number of N number of address bus or address lines. M indicate the number of data lines or data signals. So here the bidirectional arrow indicates the data lines are bidirectional, that is data, either the data towards the memory IC or data from memory IC towards the 8085 microprocessor. So usually in case of ROM kind of ICs you will find the unidirectional arrow. VCC is the input supply or excitation voltage, ground signal, and the most important signal in these two IC, that is CS bar, that is chip select, active low chip select, or sometimes you will find the name that is CE bar, that is chip enable active low input signal. So it is an active low input signal used during data read or data write operation. So suppose the processor want to read the data from the IC, or suppose the processor want to store some data in the memory. So at that time the chip enable signal must be available, or the chip enable signal must be high, that is active low. Then OE bar, that is output enable, and sometimes you will find RD bar, that is read signal. So it is an active low input signal used to read the data byte from memory location by following steps. So suppose the processor want to read the data available in the memory at the specific memory location, so he will follow these steps. So first the processor will apply the address by using address lines. Then he will make the CS bar signal active low, that is chip enable signal, he will activate. Then the processor will make the, or he will control the signal, that is read bar signal, he will make 0 to read the data from the memory location, specific memory location. And finally with the help of data bus he will read the data from the memory. So these are the steps involved during the data reading from the memory device. Next control signal, that is WE bar, that is write enable, or WR bar. So it is an active low input signal used to write a data byte into memory through following steps. Again, in this case, the processor will apply the address by using address bus or address lines of 8085 microprocessor. Then he will send the data by using data bus. Okay, so he will apply the data. Then he will make the chip enable signal active low, that is CS bar equal to 0. Then to write a data in the memory at specific location, the processor will control the WR bar signal, that is he will make WR bar equal to 0, and after that he will write the data in the memory by using data bus, or the data from processor to memory get transferred. So these are the steps involved during the data writing process in the memory IC. Then VPP. So VPP signal most of the time you will find with ROM kind of IC. So it is a programming pin normally observed with EEPROM ICs, where we are going to connect 12.5 to 25 volt to this particular pin during the programming of IC. Then PGM bar. So it is an active low input programming pin used for programming of ROM IC. So while writing a data or while writing a code in the ROM IC, so at that time this particular pin is required to make active low. So during the programming, PGM bar you have to make low, and after the data writing or code writing in the ROM, for verification this programming pin is connected to 1. So PGM bar equal to 1 after programming to perform verification operation. So these are the various signals observed with the memory IC, that is RAM and ROM kind of memory ICs. Now we will see the number of address lines required to fulfill the memory capacity. So number of address pins in memory device. So we can say that the size of the memory or capacity of the memory device we can calculate with the help of the number of address lines. So a simple formula is that to calculate the memory capacity of any IC. So suppose you are having two number of address lines. So by using the simple formula, 2 raised to number of address lines equal to memory capacity. So in this table we can able to see the first column indicates the number of address lines used, and the second column will give you the information about the memory size in bytes. So if we assume only one number of address lines, and if we put this 1 in this equation, you will get 2 byte. So in case of one address lines, you will get 2 byte memory location or memory size 2 byte. So in this way, suppose there are two number of address lines, and if we assume this equation, so 2 raised to 2, you will get 4 byte. So in this way, we can easily calculate the memory capacity with the help of given number of address lines. Suppose with a memory device, suppose 9 number of address lines are available. So suppose at that time, if we put this 9 in this equation, so 2 raised to 9, you will get 512. That is, the memory capacity of IC is 512 byte. In this way, if suppose 10 address lines are available with the memory IC, so 2 raised to 10, you will get 1024, approximately 1 kilobyte of memory capacity. So in this way we can calculate the memory capacity with the help of the given number of address lines. So suppose 11 number of address lines, so you will get 2 kilobyte of capacity. In case of 12 number of address lines, you will get 4096, approximately 4 kilobyte of memory capacity. For 13 number of address lines, you will get 8 kilobyte. For 14, 16 kilobyte. If we assume 15 number of address lines, you will get 32 kilobyte of memory capacity. And if suppose 16 number of address lines, so at that time 2 raised to 16, you will get approximately 64 kilobyte of memory capacity. So as far as the 8085 microprocessor is concerned, microprocessor provides 16 number of address lines. So if we assume all the 16 number of address lines, so at that time we can interface 64 kilobyte of memory to 8085 microprocessor. If we are assuming all 16 number of address line, that is A0 to A15, so that 64 kilobyte consists of, or that memory capacity consists of, the program memory as well as data memory. So in this way, by using this particular simple formula, we can calculate the memory capacity. Or in reverse, we can calculate the number of address lines. So suppose the memory capacity is given, suppose 1 kilobyte of memory capacity is available, then we can easily calculate the number of address lines. So suppose 1 kilobyte of memory capacity is there, so at that time 10 address lines are need to consider. For 2 kilobyte, 11 number of address lines are need to consider. So as I said, 8085 provides 16 number of address lines. So it can address up to 64 kilobyte of memory with minimum to maximum address lines. That is minimum 1 and maximum 16 number of address lines. That is 2 byte to 64 kilobyte of memory capacity. So as I said, this 64K memory space includes the program as well as data memory, that is for EEPROM and data. So user data and the code data, that is EEPROM, we can place anywhere in the 64 kilobyte of memory space. So mapping of the given memory is important in this case. So address mapping point of view, so we can place a given RAM or EEPROM of any size of anywhere in full 64 kilobyte of memory space. But we know that the reset address of 8085 microprocessor is 0000 hex. That is, after giving a reset signal in program counter, you will find 0000 data or 0000 number. So this particular 000 indicates the starting address of the program. So therefore mapping of at least one EEPROM from address 0000 hex. So EEPROM or ROM should always start from 0000 memory location, because after giving reset address in program counter you will find 0000. Okay. So while mapping, during the mapping of the ROM IC or EEPROM kind of IC, always you have to map the ROM kind of IC starting from 0000 address, and in the remaining memory space, if suppose RAM is there, So in the remaining space you can assume the RAM IC. So in these three diagrams we can able to see the mapping of the 4 kilobyte of EEPROM and 4 kilobyte memory capacity of RAM. So here in the first case, here 0000 is the reset address. So here the EEPROM is starting from 0000 and ending at address 0FFF hex. So reason behind this 0FFF address is 4 kilobyte of memory capacity. If you convert this 0FFF to decimal, you will get approximately 4 kilobyte of memory capacity. And after this particular 0FFF, the RAM IC with same memory capacity, 4 kilobyte of memory capacity, is placed starting from 1000 hex and ending at address 1FFF hex. So in this way the EEPROM is placed starting from 0000 because reset address of microprocessor is 0000, that is the program should start from 0000, okay, and the RAM is starting from 1000 to 1FFF hex. We can place this particular 4 kilobyte of memory capacity in another location, starting from another location. In the second figure we can able to see the 4 kilobyte of EEPROM is placed starting from again 0000. Always the ROM or EEPROM should map on the starting address 000 to 0FFF with 4 kilobyte of memory capacity, and here the RAM is placed starting from the address 4000 to 4FFF. If we subtract the final address minus initial address, that is 4FFF minus 4000, you will get FFF, and if you convert that FFF hex to decimal, you will get 4 kilobyte of memory capacity. So in this second example, the RAM IC placed in the memory starting from location 4000 to 4FFF. Again in the third case, 4 kilobyte of EEPROM is placed starting from 000 to 0FFF, and here the 4 kilobyte of RAM is placed in the memory space starting from address C000 to CFFF hex. Again, if you subtract the final address, that is CFFF minus initial address C000, you will get FFF. That means approximately 4 kilobyte of memory capacity. So in this way we can say that the EEPROM or RAM is always need to place starting from the memory address 0000 hex, and the final value of the memory, now in this case EEPROM, the final address is 0FFF. So this final address may get changed depending on the memory capacity. The memory capacity might be 1 kilobyte, 2 kilobyte, 3 kilobyte, 4 kilobyte, 8 kilobyte. So as far as this example is concerned, so here total 12 address lines, that is A0 to A11, are required to get 4 kilobyte of memory capacity. Okay, so 12 number of address lines are required. So which is from 0000 to 0FFF can be placed with different addresses by using remaining address lines, that is A12 to A15 address lines of 8085 microprocessor. So here mapping of the RAM and its starting address we can change by using remaining address lines. So as far as this 4 kilobyte of memory capacity concerned, we require 12 number of address lines. So suppose we are using the 12 address line, that is A0 to A11, then what about the remaining line, that is A12 to A15? So remaining A12 to A15 address lines we are going to use to map the RAM IC starting from different memory locations. Okay, starting from different memory location means, now in the third case the RAM is starting from C000. The second example, the RAM is starting from 4000. In this first example, the RAM is starting from 1000. But in everywhere you will find the same memory capacity, there is 4 kilobyte, 4 kilobyte and 4 kilobyte. So to change the location of RAM on the full memory space or remaining memory space excluding the EEPROM, we can place this RAM starting from different addresses by using the remaining address line, that is A12 to A15. Okay, we will move forward to memory interfacing, then the picture get cleared how it is possible to map the memory at different memory locations. So during the memory interfacing, following steps are need to consider. So step 1, so here you have to identify the number of address lines and number of chips or number of ICs required to achieve given memory capacity. So you have to calculate the number of address lines depending on the given memory capacity, and you have to calculate the number of ICs or number of chips required to fulfill the total memory capacity. So in the first step you have to calculate the number of address lines and number of ICs required to achieve given memory capacity. In the second step you have to draw the address decoding table, and you have to find the initial and final memory addresses, and also you have to cross check whether the selected count of address lines are correct or no. So here you have to draw the address decoding table, and depending on the question given, that is the address given, you have to map or you have to write the address in the binary format, and you have to find the initial and final address such a way that to fulfill the given memory capacity. In the third step, you have to design the address decoding logic by using either the logic gates or by using 3S to 8 decoder to generate chip enable or chip select signal for memory device. So memory IC, as we discussed a few minutes before, in case of EEPROM or RAM kind of IC, you will find the chip enable or chip select active low input signal. So to enable the memory IC or RAM or EEPROM kind of ICs, it is required to generate chip select signal by using address lines of 8085 microprocessor. So generation of the chip enable signal by using, you can design the circuit by using logic gates, or you can use the 3S to 8 decoder to generate chip enable signal or chip select active low chip select signal. And finally, you have to draw the complete memory interfacing diagram in the fourth step. So before moving towards the actual memory interfacing question, we will see the different decoding types. So first decoding type is absolute decoding. So in this particular decoding scheme, all address pins or address lines are used in decoding to select any particular location in the memory device. So that kind of scenario or decoding scheme is called the absolute or full decoding scheme or decoding technique. And the second type of the decoding is linear decoding. So in this type of decoding, all the address pins are not used for decoding. It is also called the partial decoding. So simply we can say that in case of absolute decoding, all the address pins of the CPU are used for memory interfacing, and in case of linear decoding or partial decoding,